Good afternoon, everyone. I'm Anurag, and today I'm going to be talking about Confluo, which is a distributed monitoring and diagnosis stack for high-speed networks. This is joint work with Rachit and Ian. Now, as any network operator will tell you, managing large-scale networks can be incredibly complex, with issues ranging from network misconfigurations and failures all the way to load imbalance and network congestions. And these issues are not mere nuisances, but even short-lived network outages can have severe impacts in terms of performance degradation and loss in revenue for the cloud services that depend on them. Now, fortunately, modern data center networks are equipped with a lot of information that can help in detecting and diagnosing these issues. For instance, consider a packet that traverses through a particular switch. Recent in-network techniques have essentially proposed the use of data structures that reside at these switches and can track metrics to help detect and diagnose these issues. However, due to the limited storage in the current generation of switches, another class of approaches has essentially argued for the use of in-band network telemetry techniques to embed a wide range of telemetry data ranging from packet trajectory, hop latency, queue lengths, and link utilization directly within the packet headers so that they can be finally analyzed at the end hosts. To give you a concrete example of this approach, consider the path conformance problem from the path dump paper, where you essentially want to figure out if a particular packet passed through a particular switch S1. In order to do this, you would essentially embed the switch ID whenever a packet passes through a particular switch, so that whenever the packet reaches the end host, you simply have to check the packet headers and determine if it contains that particular switch ID. Now, given that we have all of this rich telemetry data available to us, what are the goals for designing an end-host stack? First, we want to support real-time monitoring of this rich telemetry data. Then, we want to support low-overhead distributed diagnosis of network-wide events using not only the raw telemetry data, but also derived data structures such as indexes and materialized views. And finally, we want to support highly concurrent reads and writes of packet headers using minimal CPU resources. Now, the same opportunity from before, unfortunately, is also the biggest hindrance or the biggest challenge in designing the end-host stacks. Capturing line rate on even a 10 gigabit link can translate to capturing over 16 million packets per second, which gives you a mere budget of 50 nanoseconds for processing a single packet header, even with all of that rich telemetry data that's embedded within it. And in fact, when we looked at considered using open source state-of-the-art data storage systems and stream processing systems, we found that none of them even came close to meeting the packet write rates required for sustaining high-speed networks, even with 32 CPU cores. And in fact, if we used database systems that provided stronger transactional semantics, the performance overheads were even higher. If you look at the existing approaches in end-host stack design, on one end, you have traditional end-host stacks and end-host stacks that use external data processing systems that I talked about in the previous slide. They provide the required functionality for monitoring and diagnosis, but unfortunately cannot sustain the packet write rates that are required for high-speed networks. On the other hand, you have more recent custom-designed monitoring stacks, which are capable of sustaining the high-speed networks of today, but unfortunately do so by compromising either on the functionality or on the precision of the data that we want to capture. So the question then is, can we even achieve both of these properties simultaneously in the same end-host stack? We aim to answer this very question in designing our system called Confluo, where we were able to show that we can actually capture packets at line rate, even for larger than 10 gigabit links, using a single CPU core, while supporting the rich monitoring and diagnosis semantics required for debugging these network issues. And Confluo is able to do this by introducing a new data structure called the atomic MultiLog. Our main insight is that the atomic MultiLog is able to exploit structure within the telemetry data in order to meet both performance and functionality goals. For instance, we note that the attributes that we want to analyze in the network telemetry data are essentially packet header fields, which tend to have fixed sizes and are governed by rigid network protocols. And this allows us to design very specialized index structures that not only achieve the rich functionality required for monitoring and diagnosis, but also have very low indexing overheads. Second, we exploit the fact that network telemetry data has this very specific property where packet headers, once processed by the end host stack, does not need to be updated and is only aggregated at coarse grain timescales. And this allows us to use highly write-efficient append-only data structures that can support millions of writes per second. Finally, even though the analysis at even a single end host or distributed diagnosis that spans multiple end hosts does require some form of consistency semantics to ensure correctness, we note that they don't really require the full-fledged serializable transaction semantics that database systems offer, but can actually work with slightly weaker linearizability semantics. And while I'll talk about this in more detail later, I want to point out that by exploiting this particular property along with other properties, we're able to trim down the traditional concurrency control mechanisms to just updating 2 integers, which allows us to achieve even higher performance at higher degrees of concurrency. Okay, so let's dive into Confluo's techniques. The first, we'll take a look at how the atomic multilog enables write-efficient storage. We know that traditional data stores, unfortunately, have to handle more general workloads and therefore end up using complex data structures that have higher write overheads. In contrast, in the atomic multilog, we can exploit the fact that data that's once written is no longer updated and use this fact to use concurrent append-only logs to store not only the header packet logs, but also to store data across the derived data structures such as attribute indexes, packet filters, and even attribute aggregates. And the use of these append-only logs allows us to achieve write efficiency that is capable of sustaining millions of packet writes per second. But on the other hand, we give up the support for in-place updates, again, which is acceptable for network telemetry data. Next, let's take a look at how we achieve the consistency semantics in atomic multilog. We first note that database management systems essentially need to support operations where you can have arbitrary collections of operations that span multiple objects. And all of these collections of operations may need to be supported atomically. And as such, these databases need to support strict serializability semantics for their transactions, which end up having very high overheads at high concurrency. In contrast, network monitoring and diagnosis stacks have a very particular access pattern for their data. On one hand, you have the network, which performs a series of writes on unique packet headers, while on the other hand, you have the network operator, which performs several queries which assist in monitoring and diagnosis functionalities, which can be visualized as a series of read operations on the data. Now, given that we are only performing these single object reads and writes, we can actually relax the transactional guarantees to something like linearizability guarantees, which provides the required correctness guarantees, but does not have the high overheads of transactions. So if we look at how Confluo actually enables linearizability for the atomic multilog, this essentially builds on a huge body of work on linearizable concurrent logs, where the high-level idea is to essentially maintain 2 integers, a read tail and a write tail. The write tail forms the logical end of the log, and whenever an append operation comes in, it increments the write tail by the amount of data that it intends to write, and then actually proceeds to write the data. The read tail, on the other hand, forms the boundary of the data that is safe to read by the concurrent read operations. And whenever an append operation completes, it updates the read tail so that the data that it just wrote can become available to subsequent read operations. By ensuring that these read tail and write tail integers are updated atomically, we can ensure linearizability for the read and write operations. And by using lock-free techniques such as atomic hardware instructions that are readily available in commodity servers, we can ensure that these linearizable semantics can be provided very efficiently. In Confluo, we take this approach one step further, where essentially instead of providing linearizability semantics for a single log, we provide linearizability for a collection of logs. To do this, we know that we only store the packet header data at the header log, whereas all the other data structures and the other logs in the collection only store references to the header data. Now, this allows us to designate the read tail and the write tail for the header log as the global read tail and the global write tail. Now, whenever a new packet needs to be written, we first increment the global write tail, then proceed to update not only the header log, but also all of the other logs across the different derived data structures. And only once we have updated all of the data structures do we go on to update the global retail. This ensures that the operations, end-to-end operations across the collection of logs is now atomic and linearizable. In fact, we make the observation that now that we have end-to-end linearizability for the collection of logs, we don't really require linearizability for the individual logs, which allows us to relax these linearizability guarantees and enables us to achieve significant performance gains, especially at higher degrees of concurrency, which are often required to sustain the packet write rates for high-speed networks. Again, I will note that we do this by giving up on support for transactions, which again is an acceptable trade-off for network telemetry data. Okay, so finally we'll take a look at how the atomic multilog achieves efficient indexing. Now the problem with traditional index structures is that they have to support general workloads and be able to index arbitrary size attributes. And in doing so, they employ complex data structures that not only have an expensive write path, but also have expensive mechanisms to resolve conflicts between concurrent write operations. In contrast, in the atomic multilog, we only have to index fixed size attributes. In particular, these header fields that we have to index even have fixed domain sizes. So for instance, if you have a 16-bit port, it has a fixed domain which ranges from 0 to 2 to the power 16. We exploit this fact to essentially use a perfect Carey tree data structure to index these fields and only supports indexing for fixed size attributes. Each node in this tree has exactly k children, and even the depth of this tree is fixed and is predetermined by the size of the attribute that you're actually indexing. The leaves of this tree are the concurrent logs that I described earlier. Now, by using this efficient indexing data structure, we can ensure that not only the write path significantly simplified and has much more lower overhead than traditional data structures, but we can also provide very efficient resolution of concurrent write operations on the index structure. And this allows us to achieve performance that is 2.25 times faster compared to state-of-the-art lock-free data structures for indexing on a single core, and as much as 8 times faster across 48 cores. Moreover, this index structure also allows ordered access to the index data using inexpensive range queries. Again, the performance for this particular query, because of our simple index structure, is almost 5 times faster than traditional state-of-the-art lock-free data structures. Again, I want to point out that we are only able to achieve this because we have to specifically index only fixed size attributes and do not have to consider general arbitrary size attributes. Okay, so let's take a look at how the atomic multilog fits into the nhost stack. We've implemented Confluo as a part of the hypervisor, where we essentially exploit virtual switch modules to mirror packet headers at the network interface card and spray them across various ring buffers. The Confluo writer modules then pick up these packet headers from these ring buffers and then write them to the atomic multilog using the mechanisms that I described in the previous slides. We also provide a monitoring and diagnosis module, which essentially exploits the indexes and derived data structures along with the raw telemetry data to support rich monitoring and diagnosis functionality for the different debugging applications. We also provide an archival module that periodically takes all of the in-memory data structures and flushes them to persistent storage in order to relieve the memory pressure. Now, so far, I've only talked about monitoring and diagnosis in the context of a single end host, but often there will be issues where we want to diagnose network-wide events, which requires looking at multiple end hosts. To this end, Confluo uses a centralized coordinator that is capable of collecting and analyzing packet trajectories and packet telemetry data across the different end hosts in a consistent fashion using a specific and specialized linearizable snapshot algorithm. At a high level, this linearizable snapshot algorithm in Confluo ensures that every diagnostic query that spans more than one end host gets translated to a consistent snapshot. And what we are able to guarantee is that all of these snapshots are linearizable, which means each snapshot is atomic, and the snapshots are totally ordered, which means that if a particular snapshot happens before snapshot S2, then the snapshot S2 must contain all of the changes that were reflected in S1. One limitation of our distributed snapshot algorithm is that it does not consider the delays that are introduced by the n-host stack while it is ordering packets that span multiple n-hosts. We are actively working on resolving this limitation in future work. Unfortunately, I won't have time to go into the details of this distributed snapshot algorithm, but I would encourage you to take a look at our paper in order to get the details of this algorithm. Now, we have evaluated Confluo across a wide range of workloads and for a large number of application scenarios. And our results have shown that, on one hand, Confluo is able to capture packet headers at line rate for even larger than 10 gigabit links, while evaluating thousands of per packet triggers and tens of per packet filters using minimal CPU resources. And on the other hand, Confluo is able to exploit the rich telemetry data that is embedded within the packet headers in order to enable a large class of network monitoring and diagnosis applications. Unfortunately, I will only have time to go through only a fraction of these results, but I would encourage you to take a look at our paper for detailed evaluation. One of the main goals in Confluo was to ensure that we are able to sustain very high packet rates while supporting rich monitoring and diagnosis functionality using derived data structures such as indexes and per packet filters. In order to evaluate this goal, we essentially looked at the performance of the atomic multilog in terms of its packet capture rates using multiple filters and per packet indexes. If you look at this particular plot with one filter, Confluo is able to sustain packet write rates of almost 25 million packets per second, and this particular capture rate degrades gracefully as we add more indexes to the atomic multilog. The same trends are observed in terms of graceful degradation in performance as we add more per packet filters. What is even more interesting is that if we make more CPU cores available to the atomic multilog, the packet capture performance is able to scale almost linearly with the number of available CPU cores, both with multiple filters as well as multiple indexes. And this is mainly because of Confluo's relatively inexpensive linearizability and concurrency control mechanisms. Another goal in Confluo was to ensure that the CPU utilization while enabling this monitoring and diagnosis is minimal at the end hosts. And to evaluate this, we measured the CPU utilization for processing packets at line rate on a 10 gigabit link. The plots over here show the CPU utilization on a single CPU core. We see that with a single filter and a single index, the CPU utilization is roughly 75% for the smallest packet size, which is essentially the worst case for Confluo. And as we increase the packet size to more realistic values, we see the CPU utilization drops to almost negligible levels. Moreover, if we increase the number of indexes or filters, we see that there's a sublinear increase in the amount of CPU utilization at the end host. And the main takeaway here is that Confluo is able to capture packets at line rate for 10 gigabit links for a wide range of packet sizes using only a single CPU core. There are a lot of results in the paper that I have not covered here, but I would again encourage you to take a look at the paper for more detailed evaluation. But for now, I want to talk a little bit about Confluo's general applicability. Now, we have Confluo exploits three specific properties for network telemetry data. That is, it has to only analyze fixed size attributes. We have to support workloads that have append-only semantics. And finally, we do not require transactional semantics for our workloads. It turns out there are many other applications that tend to exhibit similar properties, some of which include distributed messaging systems like Apache Kafka, and time series databases such as OpenTSDB. And we're actually actively exploring Confluo's applicability for application scenarios outside of network monitoring and debugging. Also, we recently open sourced our system, and we're very pleased to find an exciting feedback from the open source community. In fact, just 2 weeks after we open sourced Confluo, we found that the number of stars on GitHub rose to 1,000, and this has been really exciting. With that, I'd like to conclude my talk. I have presented Confluo, which is a distributed monitoring and diagnosis stack for high-speed networks. Confluo introduces a new data structure called the atomic multilog, and the atomic multilog is able to exploit structure in the network telemetry data to support simultaneously rich monitoring of telemetry data, low overhead diagnosis, and high concurrency reads and writes. Thank you, and I can take any questions.
Thanks, Anurag. Questions? I'll start us off with a very low ball, not so great, but obvious and mandatory question for NSDI. What happens at 40 and 100G?
That's a great question. At 40 and 100G, it really depends on several factors. First of all, it depends on how much analysis you're doing on the data. So if you have a lot of indexes and a lot of filters, you may not be able to sustain those packet write rates using a single core. But what Confluo enables is essentially that you have very low overhead concurrency mechanisms, which allows you to exploit modern hardware and use multi-core architectures to support these workloads, essentially.
So do I understand correctly that it requires the end-to-end host monitoring? Like you need the end hosts of the flow to do the monitoring?
Yes, so we assume that the Confluo is implemented as a part of the hypervisor at each of these end hosts, and therefore we can analyze the packets to perform all of this debugging and monitoring.
So if you are focused, let's say, as a network operator, mostly on the network switches, and so this won't be able to, so there is no data that you can glean at that layer, right?
I mean, we are able to exploit the in-band network telemetry techniques that allow us to embed data from within the switches into the packet headers. But then we argue that it is more scalable to analyze them at the end hosts because of the current limitations of switches where you do not have enough storage resources. And therefore, we do exploit the information that these switches are able to provide, but only do the analysis at the end hosts.
So one other question. So a lot of the insights here are coming from the right side, what the data types that are going to be recorded are, right? Fixed size attributes and such. Have you also thought about optimizations that stem from what kinds of queries people might want to run on such systems?
That's a great question. And although we have done some preliminary analysis of the kind of queries, I wouldn't say that we have looked at those queries in detail. The biggest bottleneck that we were faced with at the time of this project was essentially sustaining the packet write rates to begin with. But again, looking forward, I think that is a pretty interesting thing to look at.
So how much value do you think there would be in it? So do you care more about, so as you said, the time to write and keeping up with the data rates as the primary constraint? How much do people care when they're looking at these systems, how long it takes to execute the queries, right? So a lot of the database optimization community does this kind of database design so that they're optimizing for the query time. Would you say that that's also one feature that makes your work different? You're just bothered about consuming, just writing the data out?
Yeah, so that's a great question again. So there are two components to these queries. There's the monitoring queries, which happen when every packet is written, and we really do need very low latency execution of these queries when the packets are written. So we do care about latency for query execution at that time, and we have optimized heavily for that scenario. In terms of query execution for diagnosis purposes, you essentially currently have a network operator doing these operations, so you don't care as much because as long as it doesn't take hours to do it, it should be fine. But looking ahead, if we have automated monitoring and diagnosis where there's an automated system that does these and resolves these issues, so it would be important to resolve that as well.
All right, cool. If there are no other questions, let's thank Anurag.
Thank you.